Thank you very much. It's a great honor to be presenting our some preliminary findings here. So our research topic is when social speech signals are not favored, enhancing the use of speech prosody in autistic children through perceptual training and human-robot interaction. So some of you might be familiar with autism spectrum disorder. So it's a neurodevelopmental disorder, and usually patients might show speech and social communication impairments, and also repetitive and restrictive behaviors. We're particularly interested in this population, and one of the reasons is it has very high prevalence rate. Recent study, it's estimated that 1 out of 36 8-year-old children actually have ASD. And we're also quite interested in the speech prosody, in examining speech prosody of autistic children. I think it's the reason is that essentially speech prosody is a very interesting topic in linguistics, and autistic children have been reported to have some difficulties in this aspect. So we think that we might be able to use the findings in linguistics to try to help them in this aspect. So speech actually conveys information not only through segmental sounds, but also through prosody. And communicative functions such as lexical and focal functions can be encoded through articulation. So in this project, we're particularly interested in focus marking. So there are many definitions of focus. This one is probably the easiest one, and it's from a functional perspective. So focus refers to an emphasis some part of a sentence as motivated by a particular discourse situation. Usually we have these focus types, such as broad focus, non-contrastive narrow focus, and contrastive focus. So here are some examples. In a conversation, like in the first one, a speaker A might be saying what happened, and speaker B would answer, Emily broke a vase. So in this kind of situation, we have broad focus. However, if speaker A asks, what did Emily break? And speaker B is likely to use some prosodic approach by saying Emily broke a vase. So you will see that there is prosodic prominence in the object here, which is the case of a narrow focus. Then in the third conversation pairs, did Emily break a glass? No, Emily broke a vase. So in this case, it's possible the speakers will be using prosodic strategies to correct information provided by speaker A. So in this case, it's called the contrastive focus. So we're particularly interested in how autistic children produce this kind of answers. It has been shown that autistic children have some difficulties in producing focus marking. And there are some common errors. Usually it's from studies on non-tonal languages. So they tend to accentuate the beginning of a sentence regardless of information structure. So no matter where the new information is, they tend to emphasize the beginning of a sentence. And if you examine the literature, you would find that the results are actually mixed. So some of the autistic individuals can mark focus, but others might not be able to mark focus. I guess it's always something quite challenging for studying this kind of population because of the variability. So when we try to search the literature, it's not uncommon that usually we will have very mixed results. And for focus marking in Cantonese, by typical population, there are also some mixed results. So some studies find on-focus F0 expansion and even post-focus F0 compression in Cantonese, but other studies suggest that prosodic prominence in Cantonese is primarily signaled by on-focus lengthening. So we are thinking about whether we can do this kind of study on autistic children, and what is special for Cantonese, and especially for autistic children to produce focus marking in Cantonese. We actually think about the potential difficulties because Cantonese is a tonal language. So in addition to producing lexical tones accurately, they have to also use acoustic cues such as F0 to show focus marking. So this might be potentially difficult for autistic children to do. So there are already papers suggesting that they might have some problems in producing tones. And if they need to further use similar acoustic cues to mark focus, that can be something that's more challenging for them. Based on the weak central coherence theory, we try to make some hypotheses. So if you're not very familiar with that, this theory basically is saying that autistic individuals tend to remember the details rather than integrating and processing information in context. So we try to apply this kind of theoretical framework in our study. So things, to produce focus, it's not only about using acoustic cues, but you actually need to integrate information from multiple levels of language. So you will need to map between the acoustic cues and information structure. So if they potentially have problems in integrating information from multiple levels of language, then potentially they might also have difficulties in using prosody to mark focus. And also the lexical tones might also be an additional challenge. So we also made this hypothesis that the lexical tones might also influence focus marking. So we collected data from both Cantonese-speaking children with ASD and also the typically developing children with matched background in age, gender, and also linguistic background, and some other standardized tests. And for the materials, we tried to design the materials to be simple enough for autistic children, because the participants we're trying to recruit should at least be able to produce a complete sentence, and then we try to design the sentence to be as simple as a description with a subject, a verb, and an object. And we also try to control the tones. So we have 6 sentences with the same tone on each word, and 9 sentences with a mixture of tones. And we also have 7 focus conditions. So we have broad focus, narrow focus, and contrastive focus with different positions. Here is an example. In order to elicit production from both typical children and autistic children, we try to let them play this under the shape game, following previous designs. So what they would do is that they would first see the figure on the left. Well, of course, before this, we will have a practice session. So they should be familiar with all these pictures, and they should know what is the subject's name, and what is the subject doing to a certain object. Then they will see a figure looking like this with the gray area covered, and then we will remove this gray area, and then experimenter, when they were still looking at this figure on the left, the experimenter will ask them questions like, who is drawing the moon? And then when this gray area is removed, the participants are expected to answer the questions. Like the subject Lola is actually drawing the moon. So before we chose this design, we have actually tried some other ways, say using pre-recorded questions and some other less natural ways, but we find probably this way is the best for eliciting focus marking in adults. So we try to use this way to elicit focus marking. And after collecting data, we use linear mixed effects models. So the fixed factors will be the participant group, whether they are autistic or not, in the position to focus, pre-focus versus on-focus versus post-focus, and also focus type, as well as tone shape. So we try to group certain tones together so that it can be easier for us to analyze. So we have non-low level tone, tone 1 and tone 3, versus rising tones, tone 2 and tone 5, and low tones, tone 4 and tone 6. Then we try to have the dependent variable inserted, which are the average F0, F0 range, duration, and intensity. So these are the acoustic parameters in the dependent as the dependent variable. Oh yeah, we also have a prosodic complexity. Because we have two conditions. One condition are sentences with the same tone, and the other condition actually has mixed tones. And we fit the model, and we also conducted post hoc analysis, and we have found that there are actually some differences in the ways the autistic and typically developing children use speech prosody to mark focus. And the autistic and typically developing children actually exhibited different strategies. At least we have found that they are quite different in the use of F0 range and duration. So our first hypothesis is actually supported. Autistic children seem to have some problems to use prosodic cues to mark focus. So typically developing children actually can make significant expansion of the on-focus syllables, but autistic children actually do not show significant expansion on the on-focus syllables. But they tend to show post-focus compression instead. And for duration, typically developing children showed clear on-focus expansion, but autistic children actually showed insufficient on-focus lengthening, but they actually showed post-focus lengthening, so which might be due to final lengthening. And our second hypothesis is partially supported. The autistic group, they could mark focus using the on-focus expansion of duration only on the low tone. So we had a category called the low tone that includes tone 4 and tone 6. We're still thinking about the reason, and it's probably because of the short duration for these two tones, and it's probably more likely for them to make it more dramatic than other tones in the focus marking. So that's the some findings on their focus marking difficulties. Then the next step is, of course, to think about what we can do to improve their use of prosodic cues in focus marking. So we have thought about lab perceptual training. So this is inspired by a second language acquisition, where it's actually found that perceptual training is usually very effective, and even if you add production training, it's not always the case that the production training is going to be more effective compared to perceptual training only. So we think actually we probably should start with lab perceptual training if we hypothesize that they might have some problems in mapping acoustic cues with information structure. Then if we can change their mapping, then probably they will be able to use some prosodic cues to mark focus. And this training is designed without social interaction. So they are exposed to many stimuli, many conversation pairs, but without interacting with without any social interaction. And then another method we're trying is we're using this robot because we believe that one of the fundamental reasons that these autistic children might have some difficulties in language is probably because they have problems in communication. So they probably don't really have the they can't really learn language well if they don't have enough social interaction. If we can use this robot to simulate social interaction, then probably it's going to improve, well, in this case, the use of speech prosody. But probably this simulated social interaction can be also beneficial in other aspects. So we're also trying and see whether we can use this robot to improve their communication skills in general. And we also tried some other methods like sound speech training. We'll see if we have time to cover, but the idea is that essentially there are many findings showing that probably the autistic individuals have some advantages in music. So we think that if we can use sound speech that can possibly mimic the speech prosody. So we actually have found a composer to compose melodies that can mimic the focus marking. And we also tried and see whether using this kind of sound speech, we can actually let them improve in their focus marking. So for lab perceptual training, there is no social interaction, and we have linguistically structured and targeted tasks to improve the mapping between acoustic cues and information structure. So we have also consulted the usual, the tasks that have been effective for autistic individuals. So usually the target, the tasks have to be structured, and also the tasks should have a specific target. So which we also try to design it according to what has been successful for improving, not necessarily in focus marking, but in speech skills in general. And we try to let them let autistic children to be exposed to congruent and incongruent pairs of conversations. And for the robot-assisted training, we have also incorporated simulated social component. So we actually need the trial participants to ask questions, and the robot will answer questions. And we hope that during the interaction, they would improve in the use of speech prosody. The advantages of using robots has also been found, that usually robots are more predictable, so we can actually design and program it to be relatively consistent and predictable. So in that way, autistic individuals might find the robots less frustrating to interact with. And there are also many studies reporting the likability of robots by autistic individuals. So there are evidence showing that there is increase in activity engagement, in also eye contact and speech engagement. But of course, that doesn't mean that if the participants like the robots, definitely they're going to improve if we're using this robot. So we do need more clinical evidence that by using robots, they can actually improve certain targeted communicative or speech skills. So that's why we're programming this robot and trying and see whether this robot can actually help them. So we have acquired this social robot. We acquired this one because this robot is actually very flexible. We have also checked other possible robots. They either have faces that's very hard to change, because usually in this area people would use motors to mimic the movement of the muscles, but we do have so many muscles that probably cannot be easily mimicked by the motors. So the movement of the face usually do not look very natural, and all these robots are quite expensive. So if you check Hanson Robotics, this is the robot Sophia they have made is already very human-like, but still when they're making facial expressions, they do not look very natural. And in order for us to make very natural facial expressions, we actually need to first investigate what muscles are involved, and then we need to program the motor so that they can mimic the facial expressions. And we think that's probably that would cost a lot of time, and also we don't really have that much funding to do that. So instead, I think this one, the fur hat robot, is actually a easier and better solution in this case, because it has a flexible it has flexible faces, because the face is actually projected. It's not it doesn't depend on any motors, and we can easily change the skin color, the placement of the eyebrows, the size of the eyes or the lips, and we should be able to adjust the facial expressions easily. And they also have some technology like lip sync. So when we have the speech, the robot can actually provide lip sync automatically. So we think that's probably something that's worth trying first. And social interaction is, of course, a key factor in language acquisition, and language learning with social interaction is actually more effective. But for autistic population, unfortunately, they process information quite differently. Because during social interaction, multisensory information needs to be processed, and then usually social speech signals might not be favored by this population. So this, well, is actually possibly one of the reasons that they might have some problems in language acquisition. So we have these hypotheses that lab perceptual training is going to improve the mapping between acoustic cues and information structure, and in turn, it may lead to better usage of prosodic cues. And for the second one, robot-assisted training, we also hypothesize that it will improve the usage of prosodic cues through simulated social interaction with the fur-hat robot. So in total, we have collected data from 83 children, including 60 autistic children and also 23 typically developing controls. And of course, we have also done all the standardized tests, like the Hong Kong COLAS, and the IQ test. For the design, we have the pre-training and post-training speech tasks being the same. And we try to elicit focus marking in these pre and post speech training tasks. And for the training, we have two methods. In this project, we're trying to compare the results from the lab perceptual training, LPT, and the simulated social interaction training, SSI. So for the stimuli, it's similar. For the pre-training test, we also have these 5-syllable subject, verb, object sentences, and we also have the corresponding figures. It's similar to the example that I have just shown you to elicit focus marking. And for the lab perceptual training, we also have 5-syllable sentences. Of course, we know that this is this is very simple, and in reality, probably, when they need to do focus marking, they will need to do it on a more complex sentence. But I guess we can start with simple sentences, and in the future we can see if they can generalize the training to more complex structures. So for the lab perceptual training, we try to design 3 phases of the training. So in the first phase, they are exposed to congruence conversation pairs. So they will actually hear a question like who is drawing the moon, and then the prosody would actually have some emphasis on the subject. So all the pairs are matched, are congruence. But in the second phase, they were told that some of the conversation pairs are matched, but others might not be matched. Say you asked, who is drawing the moon, but the answer actually has broad focus, so that can be considered as mismatched. So participants were told that the alt trial, so the first, third, fifth trials, they are incongruence, and the even trial was congruence. So they need to attend to the differences between the odd and even trials. And in the third phase, all the trials were presented in a random order. So then the participants, we expect them, after the first 2 phases, they should be able to, start judging whether a pair is congruent or not. And we will also provide feedback. And for the robot-assisted training, we try to program the robot so that the robot can finish the interaction flow like this. So the child asks the robot a question, who is flying the plane? and the robot will respond with prosodically matched or mismatched answers, and children can judge whether the answer provided by the robot is matched or mismatched, and then they will also receive feedback from the robot. So here is a video of an autistic a child doing this robot assisted training.
邊個執書包？表姐執書包。哇！你好勁啊，答啱咗啦！發生咩事啊？表姐執書包。
Well, as you can see in the video, that this autistic child is, well, he really likes the robot, and these child participants will finish all these trials using this robot, and we can check the results from the LPT, the lab perceptual training, and the robot-assisted simulated social interaction training. So for the LPT, for the acoustic cue mean duration, we have found that autistic children tend to produce longer duration after training, and for the robot-assisted training, they have also shown longer duration on the contrastive condition. For mean F0, for lab perceptual training, autistic children have shown higher mean F0 compared to broad focus. And for robot-assisted training, they seem to have developed a lowering strategy after training. For the mean intensity, the LPT group showed contrastive on-focus words had significantly higher mean intensity compared to broad focus after training. And for robot-assisted training, they have shown also the significant higher mean intensity. So the key findings probably are both lab perceptual training and robot-assisted training can potentially lead to improvement in using prosodic cues in focus marking. While the robot training may improve significantly in F0 in the post-focus position, but on-focus expansion in duration, and also some improvement in the use of intensity. The training effect of lab perceptual training is more significant on the use of duration and intensity for on-focus words. So both of the methods are actually effective, but they might improve a bit different on different cues. So we chose the lab perceptual training because it has been reported to be effective in typical population, while speech production training may not necessarily provide extra help. So similar to the positive effects on typical population, this type of training can actually modify perceptual mechanisms in autistic children. So while we think that this kind of training probably have improved the mapping between acoustic cues and information structure, so in turn, the autistic children's use of prosodic cues in focus marking in speech production has also significantly improved. And for the robot training, the social agents theory indicates that human or human-like characteristics will be more appealing to learners, which may elicit more social affective responses and deeper cognitive processing, and in turn probably it will lead to better learning performance. So theories such as dual encoding theories suggest an advantage of multimodal sensory information to help improve the memory quality and lead to better learning results. So we do see that using this robot, we did achieve some significant results. So for typical population, usually it has been shown that live interactions can reverse babies' decline in the ability to discriminate foreign sounds more than presentation of pre-recorded stimuli. And displays of videos and audio recordings may not be very effective for the learning of phonemes or words. So many studies have actually shown that live interactions are very important in language acquisition. And also a recent study has shown that on-screen presence of the instructor also led to better learning results. So even during the COVID period, if the instructor can appear, they can appear on screen, then the learning results are actually better. So live interactions are really important, but unfortunately for autistic children, they're not very good at social interactions. And they actually do not prefer social speech signals, so that might lead to decreased social and language abilities. And these social impairments can actually influence their ability to acquire language. And autistic children, they would have difficulties in processing and integrating multisensory information. So they need to process both visual and auditory information, which can be very challenging for them. And it's also very hard for them to integrate both the visual and the auditory information. So because the problems in integration, they will find social interaction very challenging. And people's behavior are usually less predictable and less consistent compared to robots. So we think that by interacting with social robot, it might provide them with a chance in practicing the mapping between acoustic cues and information structures. And also all the tasks are very targeted and structured. So we think that this might be much easier than real life situations. So in real life situations, they might hear people using prosodic cues in some conversations that might involve more complex sentence structures or lexical items that can be potentially hard to capture. And also in real life social interactions, they also need to process a lot of information at the same time, so which can be quite challenging for them. So that's what we have done to compare the lab perceptual training and the robot assisted training. Of course, I think the robot can be further used in other aspects, and probably we can also think about later how we can design simulated social interactions to improve other aspects, such as joint attention. So autistic children tend not to have joint attention, and also turn taking. So in conversations, they tend to speak all the time without letting people to enter the conversations, or they cannot really pick the social cues when it's their turn to join the conversations. So I have actually read some literature showing that after training, I think they have picked up some strategies, but that can be very unnatural. So each time they want to signal that it's their conversation partner's turn to to speak up, they need to make a gesture like this, showing please. So each time they do this, this is very unnatural. So I guess probably by programming this robot, at least we can train them how to pick up the social signals in the turn taking, say in the prosody or in the movement of the body, etc. So we can actually train them to understand the social cues, and we can also train them to to express that this is your turn, using more subtle cues rather than making gestures all the time. I think we do have, this robot have many potentials that we can keep working on. So another direction we have tried to explore is to involve more music in the interventions, because it has been shown that usually autistic individuals actually have an advantage in music processing. And of course, it's a very important element in the early human development. And musical interventions have also been shown to improve language development and social responsiveness. And probably it's also more interesting and more attractive, especially to autistic children. And there are also many studies showing the relationship between music and speech. And music training, usually long-term music training, can shape auditory processing, influencing pitch and melody recognition, so which is relevant to both music and speech. So we have also tried sound speech, which we believe that can probably bridge music and language, and well, sound speech also have acoustic similarities to speech, and also the child-directed speech. So the sounds can mimic the prosodic elements in child-directed speech. And for autistic population, they might prefer music over spoken stimuli. So this might increase their engagement and also attention, so which can potentially enhance their language learning outcomes. So we have also conducted several studies using sound speech training, but we haven't finished all the analysis yet. I think this study is based on the Mandarin data. So we have the research question: does the sound speech training have a cross-domain effect in helping autistic children? And also, does sound speech training significantly increase the number of acoustic cues autistic children is using? And also the strategies in both on-focus expansion and post-focus compression. So this study again is also on focus marking. So we have collected data from Cantonese-speaking children with ASD and without ASD, as well as Mandarin-speaking TD children as baseline. And we have also done the IQ test, the language test. So one of the challenging thing is that we don't really have a usable language test in Mandarin, so we try to follow the literature. I think one of our colleagues is actually developing the language test, so hopefully we will have a language test in the future. And we have also done the adults too, the tests. The experimental design is similar to the ones that we have seen, but it's in Mandarin, and of course we have also controlled the tones. And we have also found some significant results. Say the there is a significant improvement in on-focus expansion in the F0 range, and also some conditions in the mean F0, there is some improvement, and for the intensity, it's not really shown on the on-focus syllable. So there are some significant improvement for this sound speech training, even for training autistic children in their third language. So we're still analyzing the data from their first language. So hopefully we can also find some significant improvements in their first language. So in addition to this kind of training, we have also tried to answer some more fundamental questions. Why it is possible that we can use this robot to conduct, say, interventions. So we try to examine whether there is phonetic entrainment between a child participant and this social robot. I think this is very fundamental because it has been found that autistic children, they tend to lack phonetic entrainment in a conversation with human beings. So that means that when they interact with the human beings, their acoustic cues do not converge to their partner's acoustic cues, which is a common phenomenon in typical population. So we actually question if that's the case, that would be saying that the intervention might not be very effective because the child is not essentially learning if the child is not converging. So we decided to test whether these children can actually converge to a robot. So we tried to design some conversations. So both of them would actually look at a map, but the maps will be different. So the child and the robot needs to communicate in order to understand each other's maps. So that during the conversations, there are keywords that are designed, such as sheep or pears. So they would replicate these kind of target words when they ask questions like how many pears do you have in your map, or where are the pears. Then we analyzed these target words in different phases of the social interaction. We have found actually autistic children did show phonetic entrainment with the robot. So I think that's some good news for us because if we did find phonetic entrainment, then probably using the social robot is going to help in their speech skills. So in addition to focus marking and some more theoretical research projects, we have also tried to use this robot to tackle some challenging aspects, such as the emotional recognition. So it's well known that autistic children have problems in recognizing others' emotions or mental status. So we are also designing emotion recognition tasks using facial expressions, emotional facial expressions, and also emotional speech, as well as emotional music. So here is a sample that you can see.
What was this emotion?
Happy.
Forehead test. Congratulations, you got a point.
So because the autistic children actually have problems in facial expressions and also recognizing emotion from emotional speech and also music, So we tend to, and also the integration of visual and auditory processing. So in our training, we try to provide, again, structured and targeted tasks to train them to process facial expressions and try to integrate visual information and auditory information together. So our pilot study actually showed very promising results. So the children have actually improved in both facial recognizing facial expressions and also emotional speech and music. But I'm not really including this study here today. But I'm saying that this using this robot is potentially useful to improve in many aspects. And of course, we do need to do more research to know that how we can, improve their abilities in an effective way. Of course, we need more research to understand why they have problems, for example, in facial expressions. So some eye tracking studies actually showed that they don't really know where to look at in processing faces. So they sometimes will look at the cheeks, which are probably not very helpful. But for a typical population, they tend to focus on the eye region and the mouth region. So a project that one of our students is doing right now is trying to let the child change their eye gaze patterns, so they might be able to find ways, so we can try to let the robot demonstrate, say, the eye regions or the mouth regions more, so that the children might be able to learn that they need to focus on these areas rather than looking at other areas in facial recognition. So these are some projects that we're doing right now. We have recently also acquired a humanoid robot. So we are also thinking about training minimally verbal children, which is probably more challenging. But we really want to see whether it's possible to let them start learning gestures and then to gradually improve, in the speech. So these are the projects that we have been doing, and thank you very much. Yeah.